So here we're looking more at exponential functions. Now they do have some very nice properties. For instance, remember in the laws of exponents, your input, your x, could be any number you want, right? That was in the laws of exponents. The base, the a, had to be positive, and it couldn't be 1. But the x, the exponent, could be any number you want. And it really follows from that the domain of these exponential functions is all real numbers. When we graph it, we'll get to see what the range is, but the domain is all real numbers. And we also said, remember, that constant c is called the initial value. Now, why was that? Well, it's really just from here. And it's really based on the fact that a to the 0, right, is always equal to 1. Okay? A to the 0 is 1. That's really what we're using here. C times a to the 0 is equal to c, since a to the 0 is equal to 1. And also, remember how we said that a can only be positive and it couldn't be 1? Well, why can't a be negative? Well, basically, it's really in the next property that we would have to put restrictions on the domain and then consider different cases. For instance, let's say we consider the function f of x. Let's take something simple. Let's take -1 raised to the x. Well, then if we did f of 1 over 2, that would be -1 to the 1 over 2, which is equal to the square root of -1. This is not defined in this class, mostly because we're not considering what are called complex numbers. So that's why we can't take a to be negative. And also, again, as I said before, a can't be 1 because 1 raised to anything is 1. That's not really interesting for us. The next theorem here is also very useful. It really tells us that if you were to increase your input in an exponential function by 1, okay, and then divide it by the original function f of x, you get the base a back. In other words, if you increase the input by 1, the ratio of corresponding outputs is equal to the base of that exponential function. And again, that's what this is saying. If you do f of x plus 1 divided by f of x, you're going to get back that base a. We'll see how we can use that later on if we have a table of values that we know is an exponential function. We can get the base back using this theorem. But why is this theorem true? It's really just a straightforward calculation. Namely, if we do f of x plus 1, okay, what do we get back? Well, that's going to be c. Let me just do a little erasing, make it easier. We get c times a raised to the x plus 1. But that is equal to c times a to the x times a to the 1. But a to the 1 is just a, so really what we have is c times a to the x times a. And this is actually equal to, well, this, remember, is our f of x. So we really have f of x times a, which of course is a times f of x. So really we just proved this equation here, and from here it's easy to get this equation, you just divide. So again, what this is saying is if you increase your input by 1 unit, the ratio of outputs will equal to the base a. Linear functions, on the other hand, that doesn't happen. Whereas with linear functions, if you increase your x by 1 unit, the y values will increase by the slope. In other words, your corresponding change in y has to equal the slope. That's also easy to see. For instance, if I take g of x to be m times x plus b, let's say. Well then, so this is the slope-intercept form. I'm using, well then g of x plus 1, okay, that is going to be m times x plus 1 plus b. And that, of course, is just m times x plus m plus b. Again, what we're doing is we're distributing. And this is, of course, just m times x plus b plus m. And m times x plus b is just g of x. So we really have this. So really what we just showed is g of x plus 1 equals g of x plus m. And so, of course, then, that tells us g of x plus 1 minus g of x equals m. Okay, so let's keep going now. Here we have a table of data. We're going to show that this function is linear. And actually, it's easy to see that it is linear because from the table, if you increase x by 1 unit each time, so from -1 to 0, the y value is increased by 3. Here we have going from 0 to 1, the y value increases by 3. Here, your x value increases by 1, the y value increases by 3, and so on from here. So each time you increase your x, your y value is increasing by 3. So that tells us the slope is going to be 3. So in other words, for each x, we have f of x plus 1 minus f of x equals 3. And so that tells us the slope, m, is 3. So we have then f of x. So the function is linear, and f of x is equal to m times x. Excuse me, not m times x. Fix that. 3 times x plus b. But what is b, though? Well, remember, b is the same as f of 0. How do we get b? Well, we know what f of 0 is. It's 5. So we know that 5 is f of 0, which is 3 times 0 plus b, and that's b. So 5 is equal to b, and we get f of x is equal to 3x plus 5. So not only is the function linear, we have an equation for it. So why is this function not linear in this case? Well, notice that if we do, f of -1, no, not f of -1, f of 0, that's what I meant to write, minus f of -1, right? That's equal to 1 minus 1 over 4, which is just 3 over 4. If we do f of 1 minus f of 0, however, that's 4 minus 1, which is 3. So because of this, it can't be linear since if we increase x by 1 unit, the change in output is not the same. So we increase x by 1 unit, but the change in output is not constant. Is not constant. So because of that, this function cannot be linear.